I'm going to try to give you an overview of the big ideas that you need to be able to do motion-free responses. Most of these concepts go back to some things that we worked with pretty early in the year. Our book kind of hooked back around to some of these topics late. So a couple things here that are pretty important. Number one, remember the idea of average rate or average rate of change, which is literally just looking at a function basically and finding the slope between two different points. You're basically saying, if my function traveled at a constant pace between the beginning point and the ending point, what would that pace be? And we'll normally talk about having a point at an x value of a and a point at an x value of b. So we have a point a comma f of a, the functional value at a, and b comma f of b. Okay, so the average rate of change is really just the slope, okay? And slope, of course, is change in y over change in x. So if you really want to be algebra 1 about it, you can literally just take change in y over change in x and you'll get the right answer. Most calculus books are going to tell you it's f of b minus f of a, okay, the two y positions over b minus a, okay? Keep in mind when you're working with average rate, you're finding a slope, you're finding a quotient. So it's always going to be the y unit divided by the x. So if you've got meters on this axis and seconds on this axis, your y's would be in meters, that would be your change in y, and your change in x would be change in seconds, and you'd get meters per second. If it was velocity on this axis, say it was meters per second, then you have meters per second on the y, divided by a change in seconds on the x, and that would be meters per second, or you could rewrite that as meters per second squared, which would be an acceleration. So be careful, you're finding the rate of change of whatever quantity it is that's being graphed. So if it's a distance, the rate of change of the distance over time is velocity. If they give you a velocity graph, the rate of change of velocity over time is acceleration. Okay. Remember also, this is a way to approximate a derivative. So for example, if they give you a table of values and you've got, maybe time and distance or something like that, and at 0, maybe you've traveled a distance of 0, and at 1 you've traveled a distance of 10, and at 3 you've traveled a distance of 15 or something like that. Remember, they could ask you, for example, to estimate, the derivative of d at 2, okay? And you can see here we don't have a time of 2 here. The only thing you can do is, basically they're saying, you've got a graph here where you're going through 0, 0, 1, 10, 3, 15. They're just asking you to estimate the slope between 1 and 3. And, the best thing you can do there is just take d of 3 minus d of 1, and then divide by 3 minus 1, and just estimate the slope here. I think in this case it's going to be 2.5, and so maybe this is meters and that's seconds, maybe it's meters per second, something like that. But remember, you can estimate a derivative when you don't actually have the function. They just give you points, and these average rate of change problems are some of the easiest questions you'll see on the AP exam. So that's definitely something you'll see. Remember that you can also find values with integrals. So for example, if I give you a rate, let's say I give you meters per second on this axis and seconds on this axis. Let's say my function's doing something kind of like this. Remember that when you find an area of something, you're finding areas of squares. You're gridding it off into squares. Each of those squares would have seconds on the base and meters per second on the height. When you multiply the base unit times the height unit, anytime you're finding an integral, you're taking a base times a height, meters per second times seconds would just end up giving you the meters. And so, for example, if you have a velocity function here, if you take the integral of the velocity function over a particular interval, it's going to give you the displacement that took place over that interval, okay? Remember that distance has to be positive. So like in this case, the velocity function is positive. So the displacement in the distance should be the same. But remember, in some cases, your velocity may be both positive and negative, and you would have to take the absolute value of the velocity to get the actual distance. Or maybe you would have to figure out when the velocity is positive and when it's negative, and find all your negative velocities separately and all your positive velocities separately, and then add them up. So that's something you may see. Remember that you may be asked to estimate a distance traveled. Maybe they won't give you the equation of that curve. Maybe they'll just give you a table with some values. Remember, you've got choices like the trapezoidal rule. You can estimate areas under a curve using the trapezoidal rule, breaking up into trapezoids, doing that kind of thing. Remember, the area of a trapezoid is half the height times the sum of the bases, okay? And so you could find the functional values along here. And again, they may all be the same width, or they may be different widths, just kind of depends. But make sure you're drawing a picture so you actually end up with the correct data. You could also use, remember, Riemann sums. You can have right hand or left hand or midpoint Riemann sums. For example, here, a right hand sum, you could take this interval, and the right hand sum, you'd make a rectangle here. So the height would be coming from that value. You multiply by the width. And then the next right-hand sum, you take this interval, pick the value on the right, make a rectangle there. This right-hand sum, take the value on the right, you get that one there. By the way, if they ask you if it overestimates or underestimates, what you should say is it's a right-hand sum for a decreasing function, so it underestimates, okay? If it was a left-hand sum for a decreasing function, you'd have rectangles like this. So you don't actually say, oh, the rectangles stick out above the curve. You say the function was decreasing. V of t is a decreasing function. And what that really means is when you pick values on the left, they're going to be the high points and they're going to stick out above. So that's the kind of thing that you've described there. Okay, so of course there's all of that information. Okay, just in general, remember a lot of times you'll be given a position function or a displacement function. A lot of times they'll use s of t to represent that. Remember that the rate of change of position over time, the derivative is the velocity. So the derivative of your position equation will give you the velocity equation. The derivative of your velocity equation, or the second derivative of your position equation, if you want to think about that, is going to give you your acceleration equation. And then, of course, you can take your antiderivative or indefinite integral. You can integrate the acceleration to get back to velocity. You can integrate the velocity to get back to the position equation. Be careful in these cases, though. Remember, you're going to have a plus c, and so they're going to have to give you like an initial point or something like that, and you're going to have to figure out what c was to get back your original equation if you're going to approach it that way. Okay? Other types of things, remember that the sign of the velocity will tell you if something is going right or left. So if something is going to the right, the velocity is positive. If something's going to the left, your velocity would be negative. If something changes direction, you'd either be going from a positive velocity to a negative velocity, or a negative velocity to a positive. What that means is your velocity would have to cross through a zero. So a change in direction could occur when the velocity is zero. Now, it doesn't have to. It could be going to the right, stop, and then go to the right again. But it has to occur. Velocity would have to be zero to have a change in direction. Or I guess technically it could be undefined if you had a cusp kind of situation. But most of the time it's you're going this way, you stop, and then you go back this way. That sort of thing. So that's how you can tell a change in direction. Remember, speeding up and slowing down. Speed is always positive. Velocity can be positive or negative, and that kind of makes things a little bit confusing. So, you know, on the surface, people always think, oh, speeding up or slowing down, we're looking at acceleration. But remember, if your velocity is to the right and your acceleration is to the right, that's taking your velocity more to the right, away from zero, and yeah, that's speeding up, okay? However, if your velocity is to the left and your acceleration is taking it even farther to the left, so if you're going negative 10 meters per second and your acceleration is negative 5 meters per second squared, negative 5 meters per second every second, you're at -10 velocity, it's going to take you to -15, which is a farther value from 0, which means you're going faster, but you're just going faster to the left. So if the acceleration and velocity have the same sign, you're speeding up. If the acceleration is opposing the velocity, if you're going to the right and your acceleration is taking you back to the left, you're slowing down, okay? And also if you're going to the left, if you have a negative velocity and your acceleration is going to the right, it's taking you back towards 0, okay? So you have to look at velocity to tell your direction, and then you have to look at the acceleration to see, is it going with my direction? If so, I'm speeding up, or if it's opposing my direction, then I'm slowing down. So be careful about that sort of thing. Other things, and this last thing is really important. It's not really handled well in Forrester's book. Okay, so let's say that I give you a velocity function, okay? And let's say that my velocity function is, let's do something simple. It's the natural log of t, okay? And we're going to be looking at the interval from 1 to 10 seconds, okay? So let's say this is in seconds and this is in meters per second, something like that, okay? So the natural log function goes like this. It crosses the axis at 1. It's got an asymptote. I'm going to pick it up right here. We're doing that, okay? So our velocity is slowly increasing, okay, which means you're moving to the right, all right? So if I tell you that your initial position is 50 meters, okay? Oh, and by the way, it's not the initial position. 3 seconds into this, we're at a location of 50 meters from, let's say, where we would have been when time was 0, or home, or starting point, something like that. Okay, and I ask you to find the position, and again, they use S a lot for position, and I ask you to find the position at t equals 7, okay? You have to be very careful with this because most people say, all right, I've got the velocity equation, I want to get back to the position equation. Normally you take the derivative of velocity to get the position. I'm sorry, you take the derivative of position to get the velocity equation. You would take the antiderivative, you take the integral of velocity to get back to the position equation, okay? The problem here in this particular example, this is the natural log of t. We don't know how to take the integral of that, okay? And on the calculator part of the exam, they're going to give you cases where you may need to take an integral and you don't know how to do it by hand. You're going to have to do it on a calculator, which is why it's the calculator section, okay? And the question is, normally, if this had been v of t, let's say it had been v of t equals 3t squared, okay, something like that. You could have taken the antiderivative here, raised the power by 1, divide by the new power. Your s of t equation, your position equation, would have been t cubed plus c, okay? And then you could have said, all right, when t is 3, the position is supposed to be 50. So when I put a 3 in here and cube it and then add c, I'm supposed to get back an answer of 50. And you could work backwards and you could find out c. So 3 cubed is 27, okay? 27 plus 23 would give me 50. So c would have to be 23, okay? That's my equation. Now if I wanted to find the position at t equals 7, I could put 7 in there and be whatever 7 cubed plus 23 is, okay? It's like around 350. That's how that can work, okay? And that's what Forrester was doing in I think it was section 10.2, okay? You just took the antiderivative and you solved for c and you popped in the equation, okay? But the problem here is they didn't give us that equation. They gave us something that we don't know how to integrate, okay? And that's where this can get a little bit more challenging, okay? So here's the key. Your calculator can find definite integrals, okay? There's a way to use the definite integral to figure out what your final position is. And here's how it works. We already know the position at time equals 3, which would be right about here, okay? We're trying to find the position when t is equal to 7, okay? Remember, this is a velocity function, okay? If I take the integral of velocity, if I take the integral of something that's in meters per second, that's an area, okay? An area is going to have units of meters per second times seconds, which is going to be meters, okay? That's going to be an area there that's in meters, all right? So I'm going to go from my starting value that they give me to this ending value of 7. Okay? And again, for showing work on a free response question, if you're going to your calculator, you just need to show I'm taking the integral from 3 to 7 of my velocity equation. Okay? You don't have to say, I'm going to put this in my calculator. Just go to your calculator. You can hit the Math 9 button, and we're going to take the integral from 3 to 7 of the natural log of t. Natural log of x on my calculator. Okay? And that's about 6.326. Okay? Round to 3 decimal places. Okay? That's 6.326 meters. Okay? That's telling me from time equals 3 to time equals 7, my position changed by 6.326 meters. Okay? If you take the integral of a velocity, it gives you a displacement. Okay? In other words, the integral of a rate tells you how much change occurred over a time period because of that rate. So what you can do is you can say, that's not my final position. That's just how much my position changed from time 3 to time 7. But what you can say here is, wait, I started out at a position of 50. You can take your initial position of 50 and you can add that integral, which ended up being 6.326. Okay, that's in meters, and it tells me that my final position at t equals 7 is 56.326 meters. Okay, I used the definite integral to find a displacement, and I just added that to the initial value. Okay, and your book doesn't really have this idea. Some books call this an accumulating function. We add up the change that takes place because of a rate over an interval. Okay, but what you could say here is that the position is equal to the initial position, maybe we can call that C, plus the integral of the velocity over that interval. Okay, and you can just add that to your initial position, and basically that's going to be your displacement. That gets added to what you start at, and then you can find your final position. Okay, that idea is going to come back again and again and again. So really, really important. I wanted to make sure that I hammered that because I don't think we really ever got to see that in class. So anyway, more in a couple minutes when we look at specific free response questions.